let's do now a summary of some of the key topics of week 3, just to give you a reminder of the things we've been doing, or if you're actually watching this before you watch the video lectures for week 3, it gives you a preview of some of the things that will be coming up in a nice overview that way. So I want to start out actually by going back to quotation we did in the introduction to week 3. One of several we did, and that is, "Subtle is the Lord, but malicious he is not," one of Einstein's very famous quotations. I realized later I didn't really talk too much about it. We talked about it in the context of Einstein's religious beliefs, really sort of a cosmic religion. Believed in, as he put it, and we've quoted a number of times now, the marvelous structure of reality. And so this quote actually, though, fits in with one of the major topics of the week, and that is the Michelson-Morley experiment, because the origin of this quote was in the early 1920s. Einstein was visiting the United States, and an American experimenter had actually just released results that seemed to show there was an either wind. In other words, again, as we'll talk about, remind ourselves about here in a minute, the Michelson-Morley experiment had a null result. This experiment seemed to show a result that was actually there, a positive result. There seemed to be some effect from an either wind. And Einstein, of course, was asked to comment about this, because by this time he was getting more and more famous. And this is where the quote came from. "Subtle is the Lord, but malicious he is not." And he explained it later by saying essentially that nature hides her secrets by means of her loftiness, her essential loftiness, but not by means of a trick or a ruse. And so he believed that his special theory of relativity, which by the time of this quote was 15 years old and fairly well established by that point, that it was just too fundamental, too foundational, that it would be incorrect at that point. And he distrusted experiments much more, for a good reason in many cases, because often we think, well, if you get an experimental result, you must accept it, and therefore you have to throw away the theory. In many cases, these experiments are so difficult to do and so sensitive to many different confounding factors that you have to take into account, that you really have to be careful about just blindly accepting an experimental result. And in this case, actually, it took a number of years. This new result in the early 1920s, it seemed to be that there were some very subtle thermal fluctuations in the apparatus that may have caused the positive result instead of the null result. So just a reminder about that. It also allows us to make a quick comment about the role of the Michelson-Morley experiment in Einstein's thinking. We did talk a little bit about this earlier in one of the video lectures this week, because often the story is told that Einstein took the results of the Michelson-Morley experiment for about 15 years or so before 1905, really, well, more than 15 years, more like 18 years or so before, and built this theory on that, which is the way science should be done. You get the experimental results, you build the theory on it, and so on and so forth. In actual fact, it may be, as far as we can tell, even though Einstein probably had read about the Michelson-Morley experiment, along with many other experiments that got somewhat similar results using different methods, that it was not instrumental in his thinking for the special theory of relativity. In later years, he sometimes mentioned it, sometimes he didn't, and of course, memory can be a little hazy as you get on in years in terms of exactly what happened when you were actually developing the theory. So the role of the Michelson-Morley experiment, and one other just side comment here too, if you took the opportunity to read Einstein's June 1905 paper, you may have noticed very few, if any, footnotes there. He gives a shout out to his friend Michael Besso for the inspiration for some of his ideas, but he mentions, not by name, but he mentions that there were several experiments that seemed to show these null results. It doesn't give a footnote for it, and so some people point to that and say, well, he wasn't giving them credit, right? He was trying to take all the glory for himself. You have to remember, 26 years old, really not in the academic world at this point, and moreover, working 6 days a week, and the libraries were only open when he was working. So he really didn't have easy access to libraries to look things up and so on and so forth. And then there was his whole approach. He was not building it on experimental results, but certain theoretical asymmetries. So that really brings us to Einstein's starting point for his special theory of relativity. We talked about in 1905 this psychic tension he was feeling. He did express it that way. And then his conversation with Mikhail Besso, and he came back the next day and then later on described it as he realized that time was suspect in some fashion. And in fact, next week, that will be a major topic for us to see how his results and his two postulates here go into the whole idea of time being suspect and how that gets worked out. But that's for next week. So his conversation with Mikhail Besso, within 6 weeks, he had published his paper in June 1905. Again, we talked about it, and hopefully you saw this if you read the paper or skimmed over the paper. Early on, he talks about these asymmetries. He gives the example of a magnet and a coil, a bar magnet moving toward a coil. And physicists is well known that generate a current flowing in the coil. But physicists gave two explanations. One if the magnet was moving toward the coil, and one if the coil was moving toward the magnet. One involving an electric field, one a magnetic field. And that bothered Einstein. He felt there should be one explanation there, not two separate explanations for something that's essentially the same. The two things are moving together. And so that bothered him because it went against the principle of relativity, right, which was a big topic in week 2. But there's this other principle. So that was one of his two postulates, the principle of relativity. The second postulate was what he called the principle of light constancy. Well-known result from electromagnetic theory that essentially said, and wave theory, that essentially said, if you have a moving source of a wave, say a light wave, a light beam, say a flashlight that's moving toward you, or a paddle device generating water waves that's moving toward you, the velocity, the speed of the wave would not be affected. And so that really led us into the notion that we need to learn a little bit more about some key wave facts so that we can understand how this second postulate, this principle of light constancy, fits into Einstein's arguments here. So we spent some time on a few words about waves. Probably by the time we were done, maybe it was more than a few words about waves. We talked about wavelength, frequency, period, phase, how you can get constructive and destructive interference if two waves coming together are just out of phase with each other or exactly 180 degrees out of phase with each other. If they're in phase, meaning the peaks and the troughs all match up, you get constructive interference, so it essentially magnifies the wave. If it's destructive interference exactly out of phase, then it negates the wave. It gets rid of the wave. It cancels out. So we talked about some of those key definitions, really, and characteristics of waves. And then we cited 3 key facts about wave speed. Okay? One key fact was that, or is that, the speed of a wave depends on the medium. So a water wave, the speed of the wave through the water, the speed of the disturbance traveling through the water, still water, say, is going to depend on the characteristics of the water itself, characteristics of the fluid. If you replace the water with some other fluid, you'll get a different speed for the wave. So speed of the wave through the medium depends on the medium itself. Second key fact, which actually we just cited, is Einstein's principle of light constancy. In other words, a moving source of waves does not change the velocity of the waves. Examples would be, again, if you have, say, some paddle device that's generating waves, and if that then starts moving toward you, if you're in the swimming pool, say, and this paddle device is generating waves and moving toward you, the speed of the waves through the water to you is going to be the same, and past you, it's going to be the same whether that paddle device is just sitting still over there or it's actually moving toward you or even away from you. In all cases, the speed of the waves past you is going to be the same. Okay? Same thing with well, we also did an example of a train whistle or train horn, that if the train is coming toward you, that the sound waves from the horn will reach you in the same amount of time. It's the same speed as if the train is just standing still. Now, we did talk about the Doppler effect in that it will affect the frequency and the pitch of the waves, but it does not affect the speed of the waves. And for light, imagine a flashlight over there. If I have a device where I can measure the speed of the beam of light going past me, if the flashlight is stationary, I'll get speed of light. If the flashlight is moving toward me, I do not get a faster speed for the speed of light. I get the same speed. So in that case, that's just a result from basic wave theory, and more particularly for light waves, the electromagnetic theory, going back to Maxwell, James Clerk Maxwell. So that was the second key fact. The principle of light constancy, a moving source for a wave does not affect the velocity of the wave. Third key fact is that a moving medium does affect the velocity. Let me say just a few words about this because as I look back on the video, I'm not quite sure it was as clear as I could have made it. But let's imagine we're in the swimming pool again. Okay? And I've got the paddle device over there. Okay? It's generating waves. Right? And so they're coming by me at some velocity, and I can measure that. If the whole swimming pool is moving, okay, so now maybe I'm in a river or something like that, or just whatever, there's a current in the swimming pool if you have one of those fancy swimming pools. If the whole medium is moving, if all the water is moving and it's sitting over there generating waves, then yes, the waves do go past me faster. Okay, so the velocity of the medium, the speed of the medium moving by, plus the speed of the waves through the medium. Okay, so when we talk about wave speed, we mean the speed through the medium, but then if I'm, again, measuring the whole thing, it's the speed of the medium flowing by me, plus the speed of the waves through the medium, faster wave velocity. Or, of course, if it's sort of going upstream, if the water is flowing this way and the waves are coming this way, then the waves going by me will be slowed down a little bit. So those were the three key facts about wave speed. The wave speed does depend on the medium, that a moving source does not affect the speed of the waves going through the medium. That's the principle of light constancy that Einstein cited as his second postulate. And then this idea that a moving medium will affect the speed of the waves. And that brings us then to the Michelson-Morley experiment. Because remember the idea of this, or if you haven't watched it yet, this is what we'll be talking about. As the Earth moves around the sun, presumably it is moving through the ether. The ether being the so-called luminiferous ether, the idea that light is a wave. There's got to be some medium through which it travels. Therefore, it is, we'll call it the ether. Actually, the whole idea of the ether goes back thousands of years, but developed at this point into the idea of a luminiferous ether. And so, again, the idea is as the Earth moves around the sun, it must be moving through the ether. And therefore, if you're standing on the surface of the Earth, you must have an ether wind, an ether breeze flowing past you. Can't feel it, but it must be there. And we must be able to do an experiment maybe to detect that ether wind. And that's what Michelson and Morley were trying to do in the 1880s. And we talked about the actual sort of layout of the experiment using airplane trip as an example, where the plane is going first headwind, tailwind round trip, and then a crosswind round trip, because that's essentially what Michelson and Morley were doing with light. They took a beam of light, split it into two beams, and sent them on two different paths. One beam essentially went headwind against the ether, and then tailwind with the ether back to the original starting point. The other beam went crosswind with the ether. And we did an analysis showing that the headwind-tailwind case takes a little bit longer than the crosswind case does. And so that's what they were trying to measure. Essentially, if the ether wind is going by us as the Earth goes around the sun, then we should be able to see this effect that light going against the ether wind and then coming back again versus light going crosswind with the ether wind, there should be a slight time difference. So if you split the beam, send it off on its two paths, and bring it back together again and measure that time difference, then we should see the effects of the ether. Problem was that the time difference was so small, about 10 to the minus 16th seconds, they didn't have the technology that could detect it. But they did. Michelson, brilliant experimentalist, and he had come up with a technique where instead of measuring the time difference as the two waves recombined, he would look at the slight phase difference between them. Because if one light beam is slowed slightly compared to the other, then when they come back together again, they'll be slightly out of phase. And that will provide an interference effect, which Michelson and Morley's experimental techniques could detect. So they set it up, and what did they find? Well, as we talked about in the video lecture, they got a null result. A fairly substantial null result in that they're expecting to see a fringe shift, as it were, due to this interference effect of maybe about 0.3 or 0.4 fringes. and they got a result that was less than something like 0.0005 fringes. And this was a huge problem because it was like, where is the ether? Where is the effect of the ether? It's got to be there. You've got to have the ether so you have light waves. The light waves have to travel through something. They have to be a disturbance through some sort of medium. And so one idea was, well, maybe at the surface of the Earth there's a drag on the ether. Somehow the Earth itself drags the ether along, so we're sort of like in a pocket. Even later on, some ideas were that they did their experiment in a basement to try to protect from all external influences and vibrations and things like that. Maybe just by being down in the basement, the ether doesn't flow through basements as well as up on the surface or something like that. Or up on mountains. Later experiments were done on mountains as well. So the whole question is, maybe there's this ether drag effect. Maybe that's the explanation for this null result, why we don't see the influence of the ether wind that should be there on the velocity of light in our experiment. The problem was there were other experiments that showed pretty clearly there is no ether drag effect at the surface of the Earth. And one of them we talked about was stellar aberration. Actually, the other one we talked about was stellar aberration. And the idea there was that starlight coming down from a star, say toward a telescope at the North Pole or near the North Pole, if there's an ether drag, then we should just be able to point the telescope directly at the star, say straight up. And the light will just come right down, okay, into the telescope. Because actually, the Earth is moving around the sun, so the ether and really everything is moving along so that you don't have to tilt the telescope. The light comes straight down. And we drew some pictures of that and to get a better idea of that. Turns out, though, as long ago as 1720s, an astronomer named James Bradley was looking for something else. He was trying to determine the distance to stars, but he discovered that actually you do have to tilt your telescope slightly, and that was evidence that there was no ether drag, that the Earth actually moved right through the ether. And we use the example of sort of running through raindrops. You've got to tilt your umbrella a little bit if you don't want to get wet from the raindrops falling up ahead of you. Same thing here. The light really coming from that star, imagine I'm on the Earth here, I'm moving this way with my telescope, and the light from the star is coming down, and it's going to land right here, okay? But my telescope, I've got to catch it when it's right here. The light's coming straight down, hitting right here, so I need to enter my telescope, so because the Earth is moving, when the light gets down here, the bottom of my telescope, say my elbow is going to be here at this point. But to catch the light coming in, my telescope, the opening of the telescope has to be here, so I have to tilt it slightly. So as the light's coming down, my telescope just catches it here, and then the light's still coming straight down while my telescope is moving like this. And so when the light actually hits it where it's going to be, my telescope, the bottom mirror is at that point. I don't know if that's better than the picture I drew in when we did the stellar aberration video lecture or not, but that's the basic idea that you have to tilt the telescope. There's this aberration effect, stellar aberration effect, very small in terms of the tilt, certainly not like that, just a very small angle, but definitely measurable. And therefore, that was indication the Earth does not drag the ether along. So you had this real problem because you had good experimental results that said that there's no effect of the ether wind, and therefore maybe the ether is dragged, but you had other experimental results that said the ether can't be dragged by the Earth. So some solutions to this, some ethereal solutions. I think I realize also I've been inconsistent in my spelling of ethereal. Sometimes I spell it E-A-L, sometimes I-A-L. E-A-L might be slightly preferred, but I'll try to be consistent here. It doesn't really matter too much. So if you notice that, I hope it didn't bother you too much. Anyway, ethereal solutions. Lorentz-Fitzgerald contraction. The idea here was originally suggested by Fitzgerald and then later by Lorentz in a more sophisticated mathematical fashion. But the idea is this, that if matter, regular matter like the Earth, is made up of electromagnetic type of forces and particles and later on maybe electrons and so on and so forth, there should be an effect perhaps of matter moving through the ether. And in fact, they hypothesized that there'd be a slight compression. If an object was moving through the ether like this, there'd be sort of like friction. It's not really friction, but that's the idea. So there'd be a slight compression of that object as it moved through the ether. And by applying this to the Michelson-Morley result, they could show that that slight contraction in the length of the Michelson-Morley apparatus perfectly made up for the slower headwind-tailwind effect that should be there, and it all cancel out, and that's why you get the null result. And so it's called the Lorentz-Fitzgerald contraction. They were also playing around just a little bit, Lorentz and also Henri Poincaré, great French physicist and mathematician, of what I've called here the mathematics of time. The idea being that in these, again, very sophisticated theories, they were trying to put it all together, and they realized, well, maybe if we have sort of this hypothetical abstract notion of time that's slightly different in certain cases, not in reality, of course, but just in the theory, then things worked out better. And so they were playing around maybe with the idea that something was a little screwy with time, but they hadn't actually gone beyond just sort of the mathematics of it. And so then that's when Einstein comes in. Einstein's solution essentially is to take the two postulates here, the principle of relativity, or really the two principles, and make them postulates as the basis for his theory. Principle of relativity and the principle of light constancy, which seem to be in conflict with each other, because remember the principle of relativity says essentially there's no absolute frame of rest. You can't define that. Constant velocity of motion is relative. I'm motionless, so somebody goes by me and I see them with some velocity, but as far as they're concerned, with respect to their frame of reference, they're motionless, and I'm the one who's moving. And so principle of relativity would say no absolute frame of rest, no absolute frame of reference, or absolute state of rest. Principle of light constancy, however, said that there's an either. And if there's an either, therefore, we can take that as a state of absolute rest. And that's the inherent contradiction of the two postulates. Einstein said, I'm going to take them both as true and see what the implications are. And so one really big implication that came out of it that we showed when we talked about Einstein's solution here is that when you combine those two postulates together, you find that the speed of light is constant for all observers. Okay? And what that means is, remember, let's say we have the flashlight moving towards us again. The principle of light constancy says the light moving toward us, if we measure the speed, and the flashlight's moving towards us, we still get the same speed for light. But now the combination says, even if the flashlight is stationary, and I'm the one who's moving, so I'm moving through the medium, right? Speed of light is still constant. And that's the weird thing, as we will see in more detail next week, because according to one of our key facts about wave speed, that's not how normal waves work. If I'm moving through the medium, I should see a difference in the speed of the wave. And Einstein, by combining the two postulates, the principle of relativity and the principle of light constancy, came to the conclusion that no, light is different when we're talking about light as a wave. It actually is constant. The speed of light is constant no matter how you're moving, whether you're moving toward the flashlight over there, the flashlight's moving toward you, or some combination of that. Speed of light is always the same. It does not change when the medium supposedly is moving, and therefore one of Einstein's famous lines in the paper, you may have seen I point out, he almost as a throwaway line, he says, note that this means the either is really superfluous. It is a concept we don't need. And again, a lot of people say, what? How can that be? We have to have the either. How else do you explain light waves going through space? We need a medium by which the wave actually travels. But Einstein, starting from these two basic postulates, said, no, I'm not going to worry about those aspects of it. I'm going to focus on these results based on two very fundamental postulates, that the speed of light is constant, and therefore, as we will see next week, we run into things such as time being suspect, the relativity of time, and get into things as really where the weirdness begins, things like time dilation, length contraction, and the like. So that's, I don't know how brief that was, but a summary of key topics in week 3 and a few other points besides that. So if you haven't watched the video lectures, now you have an idea of where they're going in week 3, and we'll fill in some of the details as you watch them. Or if you have already watched them now, sometimes it's a nice summary to put all that together and get that overview and maybe realize I need to go back and watch this or that a little bit more. So, week 3 summary. As I said, next week we really start to get into the meat of the theory and the weird results that come out of just taking these two postulates as true.